Imagine showing a handwritten number to a computer and asking it to identify the digit correctly. Humans can instantly recognize a handwritten 5 or 8. But for a computer, an image is nothing more than a collection of numbers. In this video, we'll build a neural network that learns to recognize handwritten digits from 0 to 9 using PyTorch. Let's see how it works. Before training our neural network, we need a large collection of handwritten digits. For this purpose, we use the famous MNIST dataset. MNIST contains handwritten examples of all digits from 0 to 9. The dataset consists of 60,000 training images and 10,000 testing images. The training images help the neural network learn patterns. The testing images help us evaluate how well the model performs on unseen data. Each image contains a single handwritten digit. Although humans can easily recognize these numbers, the computer sees them very differently. Let's take a closer look at one example. How exactly does a computer interpret this handwritten digit? Let's focus on a single handwritten digit. To us, this clearly looks like the number 5. Humans instantly recognize the shape and identify the digit. However, computers do not understand handwritten numbers the way humans do. The first step is converting the digit into an image. In the MNIST dataset, every image has a size of 28 pixels by 28 pixels. This small image will become the input to our neural network. A computer does not actually see a handwritten digit. Instead, it sees a grid of pixels. Each image contains 28 rows and 28 columns. That gives us a total of 784 pixels. Every pixel stores a numerical intensity value. A value close to 0 represents a dark pixel. A value close to 255 represents a bright pixel. Together, these pixel values form the image. To a neural network, a handwritten digit is simply a collection of numbers arranged in a specific pattern. The network's job is to learn patterns inside these numbers and determine which digit they represent. At this point, our image contains 28 rows and 28 columns of pixels. That means we have a total of 784 pixel values. However, a neural network cannot directly process a two-dimensional image. The image must first be converted into a one-dimensional list of numbers. This process is called flattening. After flattening, the 28 by 28 image becomes a vector containing 784 values. These values will become the inputs to our neural network. In PyTorch, this data is stored inside a tensor. The resulting tensor has a shape of 784. Now the neural network can process the image as numerical input. Next, we'll feed these values into our neural network and build the model architecture. The flattened image contains 784 values. These values become the inputs to our neural network. Our network contains two hidden layers. The first hidden layer has 128 neurons. The second hidden layer has 64 neurons. Finally, the output layer contains 10 neurons. One neuron for each possible digit from 0 to 9. As data flows through the network, each layer learns increasingly useful patterns from the image. The final layer produces scores that help us determine which digit is most likely present in the image. Now let's implement this architecture in PyTorch. We create a class that inherits from nn.module. Inside the constructor, we define the network using nn.sequential. The first linear layer transforms 784 inputs into 128 features. A ReLU activation function introduces nonlinearity. The second linear layer reduces 128 features to 64. Another ReLU activation is applied. Finally, the output layer produces 10 values corresponding to the 10-digit classes. The forward function defines how data flows through the network during prediction. Now it's time for the forward pass. In PyTorch, the forward pass happens when we call the model using the input images. The flattened tensor containing 784 values enters the network. First, it passes through the initial linear layer. Then the ReLU activation function introduces nonlinearity. The data continues through the second hidden layer and another ReLU activation. Finally, it reaches the output layer. The output layer produces 10 scores, one for each digit class. The largest score represents the model's prediction. In this example, the highest score corresponds to digit 5. The network predicts that the image contains the number 5. The forward pass gives us predictions, but we still need a way to measure how good those predictions are. In PyTorch, we use a loss function for this purpose. For classification problems such as digit recognition, a common choice is CrossEntropyLoss. The model predicts digit 5, but the actual label is 8. Since the prediction is incorrect, the loss value becomes large. A large loss indicates that the model made a significant mistake. Now imagine the model correctly predicts digit 8. In this case, the loss becomes very small. A smaller loss means the prediction is closer to the correct answer. During training, our objective is simple. We want to reduce the loss as much as possible. But how can the network know which weights caused the error? That's where backpropagation comes in. The loss tells us how wrong the prediction is. But the network still needs to determine which weights caused that error. This is where backpropagation comes in. In PyTorch, backpropagation is performed using the backward method. Starting from the loss value, the error signal travels backward through the network. As it moves backward, PyTorch computes gradients for every parameter. A gradient tells us how much a specific weight contributed to the error. Mathematically, a gradient is the partial derivative of the loss with respect to a weight. Fortunately, we don't have to compute these derivatives manually. PyTorch's autograd engine automatically calculates all gradients for us. Once these gradients are available, we can update the weights and reduce the loss. The next step is using those gradients to improve the model. At this point, PyTorch has calculated gradients for every weight in the network. However, the weights have not changed yet. The optimizer is responsible for updating those weights. When we call optimizer.step, PyTorch uses the gradients to adjust each parameter. The goal is to move the weights in a direction that reduces the loss. The amount of change depends on the learning rate and the gradient value. Mathematically, the new weight equals the old weight minus the learning rate multiplied by the gradient. After updating the weights, we call optimizer.zeroGraduate. This clears the gradients from the previous iteration. If we do not clear them, gradients would accumulate and training would become incorrect. Now one complete training step has finished. The same process is repeated again and again for every batch of training data. At this point, we have all the pieces required to train a neural network. The training loop repeatedly performs the same sequence of operations. First, the model performs a forward pass and generates predictions. Next, the loss function measures how far those predictions are from the correct labels. Then backpropagation computes gradients for every parameter. The optimizer uses those gradients to update the weights. Finally, the gradients are cleared before the next iteration. This entire process is repeated for every batch in the training dataset. Once all batches have been processed, one epoch is complete. Training typically runs for multiple epochs. With each epoch, the model gradually improves its weights and becomes better at recognizing handwritten digits. At the beginning of training, the model makes many mistakes. As a result, the loss value is high. After every batch, the network updates its weights using gradients. Over time, the model becomes better at recognizing patterns in the handwritten digits. As the predictions improve, the loss gradually decreases. A decreasing loss is one of the strongest indicators that learning is taking place. Notice how the loss drops from more than 2 down to a much smaller value. At the same time, the model's accuracy continues to improve. This shows that the network is successfully learning from the training data. Once training is complete, we can use the model to make predictions on images it has never seen before. At this point, training is complete. Now we want to use the trained model to make predictions on new images. Before making predictions, we switch the model into evaluation mode using model.eval. This tells PyTorch that training has finished. Next, we use torch.noGraduate. Since we are only making predictions, gradients are no longer required. This reduces memory usage and improves performance. The new image is passed through the trained neural network. The output layer produces 10 scores, 1 for each digit class. We then use argmax to find the highest score. The index of the highest score becomes the final prediction. In this example, the model correctly identifies the digit as 7. This is the same process used in real-world AI applications, where trained models make predictions on unseen data. You started with a dataset containing thousands of handwritten digits. Using a data loader, the dataset was divided into batches for efficient training. We then built a neural network using PyTorch modules. During the forward pass, images flowed through the network and produced predictions. The loss function measured how far those predictions were from the correct labels. Backpropagation calculated gradients for every parameter in the network. The optimizer used those gradients to update the weights and reduce the error. By repeating this process across many batches and epochs, the network gradually learned meaningful patterns. After training, we switched to evaluation mode and used the model to make predictions on new images. This is the complete machine learning workflow used in countless real-world AI systems. Congratulations! You have successfully built and understood your first neural network in PyTorch. ODI, we trained a neural network to recognize handwritten digits. While this project may seem simple, the core ideas are used throughout modern artificial intelligence. Computer vision systems use neural networks to understand images and videos. Medical imaging models help doctors detect diseases from scans. Self-driving cars use deep learning to understand roads, vehicles, and pedestrians. Face recognition systems identify people from photographs and video streams. Large language models such as ChatGPT are built using advanced neural network architectures called transformers. Although these systems are much larger and more complex, the fundamental concepts remain the same. Every model performs a forward pass. A loss function measures error. Backpropagation computes gradients. And an optimizer updates weights. The foundation you learned in this project is the starting point for understanding modern AI. Keep building, keep learning, and continue exploring the world of deep learning.